they're not much more complicated, mind you, just a little more complicated. And you'll see why in just a few brief little discussions here. There are three things I think I need to add to this, though, so that we have a complete picture. One of them, I don't know how this slipped past what we were doing, but we probably should take a look at this. Tell me real quick, if I wanted two current carrying wires to pull themselves together, would they be like currents or unlike currents? Yes, sir.
Like currents?
That's right. Like currents attract, unlike currents repel. So if you would, in your notes, draw yourself a pair of like currents. I'll do my best to do so here too. They just keep filing in late. Oh, it's Tyler. They just keep interrupting me late. Anybody notice how it was almost just straight pandemonium yesterday between the two lunches? Or was I the only one who noticed that?
What happens when they do a fire drill during lunch?
Right at the end of lunch. We lost 20 minutes the fourth period because of that. All right, so I'm drawing the currents that they're both going up. And let's say that they are a distance d apart. What is the force of attraction between the two wires? We did all that work to figure out how to determine the magnetic field from a current carrying wire. We did all that work back when we were talking about the force on a current carrying wire from a magnetic field. But this mutual attraction or the mutual repulsion, it doesn't matter which one we study. We didn't do any work on it, but we probably should. There's a force on one of the wires from the other, but we can put it all in terms of the current and parameters of the magnetic field. For example, we know that the force on a current carrying wire in a magnetic field is IL cross B. And of course, the right-hand rule would help us lay out that force, they just keep on coming in. Good morning. I assume you have a pass?
No, please not.
Let's keep trying here. If we have the two currents so that they are parallel, I think that we could dispense with the cross product. That's just a formality there. And that gives us ILB. Now, L has to represent how much of the wire is actually in that magnetic field. So right now I would say the wires are L long, or at least the parallel portions of the wires are L long. So our next response is, well, we have a way of expressing B in terms of the current. In fact, we could determine the size of the magnetic field that must exist right here at the point where the wire is. We know it's into the page. Well, some of us know that it's into the page. Those of us who have figured out how the right-hand rule works can figure out using the whole curl rule that it's into the page right there. So those yellow X's, that's the magnetic field. And also, using Ampere's law or something similar, we could probably figure out the size of that magnetic field. And after all of our discussion the last couple of days, it comes down to whether this has a pi in it or doesn't. So does this one have the pi or does this one not have the pi? Which is it? This one does have the pi, that's right. So squeeze that in right there. So force equals I L mu naught I over 2 pi d, which produces this interesting effect, I squared L mu over 2 pi d. Now, not terrible, I don't think. But you know how I like to make comparisons. If I had two charged particles and I want to see the force between them, the two charged particles would be, Q squared over 4 pi epsilon naught d squared. right? If they were a distance d apart, I'd have a similar calculation. I don't think it's, too weird that you have this charge squared from Coulomb's law, and we get I squared for two currents. So I don't think that's too weird. I mean, obviously, the L and the D have to make a play here. But the fact that, the D is squared there, it's a little different. So I'd say we can indicate that force between the two charges is two currents is going to be a little stronger. Another interesting result here, and I'm not sure that you guys realize this, but if I had two wires that were, let's just, as a drawing goes, I just draw it like this. Not two wires, but one wire loop, where this was connected to a battery, but the wire was free to move. So perhaps the wire's on like a frictionless surface, but the two ends of the wire are connected to a potential difference. This will maintain a current passing through the wire. And in the way that I've drawn it, the current would look like this, right? And there'd be a current over here. What do you think would happen to this wire? Luke knew right away. What do you got? Yeah. Now, if you think about it, what shape would it make? Yeah. You put a wire just in space and run a current through it, it's going to form a circle. The wire has to be a loop anyways, in order for it to meet up with both sides of its potential difference. But because unlike currents repel, there will be a not uniform, because the force here will depend on how far apart the pieces of the wire are, but there will definitely be a force all along the wire, everywhere on the wire, repelling it from all the other parts of the wire in such a way that, it'll spread out till it forms a circle. So, just a couple little things about currents before we go on to the electric motors. Any questions about any of this? Now, I didn't cover it explicitly. I know that it's, I asked you some questions about it. By the way, so again, side view, top-down view. And the side view is a cutaway view. Everybody ready? All right. Looking at the top-down view, I think we already know the answer to this from yesterday, but I want to make sure I'm a little proactive, and I want to make sure all of you right-hand rule this portion of the problem. It might be easier to turn your paper to orient it in a way that is helpful for you. But please don't have me call you out for you to give me the wrong direction for the force on our current carrying loop. Okay, I think we can go through this now. And as I did yesterday, I'm going to do this in red because I know it's very light. 1, 2, 3, 4. And I don't need to do 5 because 5 is the same as 1. So let's go with Adi. What's the force on wire segment 1? What's that? Swing and a miss. Wire segment 1. Are we looking at the same wire segment? This one right here? Yeah. All right. So wire segment 1, current's this way. I cannot rotate my wrist to put my middle finger in the same direction as the magnetic field. All I could do is recognize that the magnetic field is 180 degrees in the opposite direction. The sine of 180 would be 0. So there is no force on this top piece of wire. Take a minute, correct your work for the rest of you, because I know who to call on to get the wrong answers. I've done it remarkably well. Owen, can you tell me the force on segment 2?
It's
Out of the page. That is correct. So the force on wire segment 2 will be out of the page. Now, take a moment, look at the side view. In the side view then, what direction is that? We all agree it's up. Now you can, of course, right-hand rule it just to make sure. It's hard to do it with your paper. It's easy if I just stand here and do it, but that's what it should look like. Current coming out of the board, magnetic field to my left, your right, my thumb points up, so the force on that wire segment is upwards. Question about that? All right. So, Chase, wire segment 3?
Segment 3 would have no force on it.
No force on segment 3. And wire segment 4, let's go with Ava. Into the board, that's right, into the board. Thank you all. That would mean downward. Correct? All right, for just a moment, let's side shift into mechanics. This wire loop constitutes a lever arm, and as such is experiencing 2 torques. Based on the dimensions I've given here, please express the size of the torque in the variables that are here. I'll give you 60 seconds. I'll go even 3 minutes. So we have a torque arm length of S over 2, and we have a force that would be calculated as ILB. Good so far? All right. Not so bad. And I think we can kind of go a little further with this now. What am I going to substitute in for L here? That's right, because it's the length of the wire exposed to the magnetic field. It's a square. So S will work just fine. So my expression then changes to ISB sine, what's the angle in this case? 90 degrees. Let's be careful about that for a minute, okay? And just for a minute, this angle is the angle between the current and the magnetic field. There's going to be another angle in a minute that we do need to be careful about. Because the torque is R cross F, or RF sine phi. This angle is the angle between the force and the torque arm. Now, let's just start, but keep in mind, I don't think we can throw this away. I think we need to pay attention to it. So let's start by building our torque here. S over 2 is going to be our torque arm length. So R is going to be S over 2. The force, we know, is now ISB sine 90. So I'm just going to put ISB. And then I think we need to leave this sine phi in here for now. Now, this is just one torque acting on the wire. How many torques are actually acting on the wire? 2. There are 2 torques that act on the wire. So twice this is our net torque on our current loop. So this page is awful messy, but I need to be able to draw on the diagram still, and I don't want to redraw it. So I'm going to take away what's on the right. No, I'm not. I thought I was going to, but now I will. Okay. So consider for a moment that the net torque is going to be 2 times the individual torques because they are going to be the same size and they act in the same direction to cause a into the page rotation or into the board rotation or simpler clockwise rotation. We all good with that? I need everybody to be on board here because when I challenge you in front of the class, you don't want to look like an idiot. Okay? So that produces I s squared b sine phi. This isn't an accident, right? It's not an accident. In fact, I want you to see that it's not an accident. This is the area of the loop. This is going to come up a couple of times, but our shape doesn't have to be square. No matter how you do this, you will always find that you get the area here, even if you do some kind of odd shape. Most of our wires are going to be in loops. They're going to be circles. And I want you to imagine a circle in this would experience a non-uniform force because the wire's not passing the same way, doesn't have the same torque arm length, all of that. But it won't matter. No matter what the shape is, it ends up being that the area of the loop will show up here every time. This is the torque on any loop in a magnetic field. The area shows up because the length of the wire and the distance from the center of the mass or center of the rotation always shows up in this way. Now, that's not all I want you to know, but it will help. The next thing you have to recognize is that this system rotates. So this wire and this wire begin to move in a circular path because they are affixed to the square and will eventually be, say, here and here with the currents still in play. The force, however, and you should verify this, stays in the same direction. You should verify that. Right? No matter where it is, out of the board, magnetic field to the right, my thumb still points up, into the board, magnetic field to the right, my thumb still points down. Which means that the torque is decreasing as the loop turns. So that if this line connects the two of them, this angle, which is phi here and phi here, is making for a smaller and smaller torque. This isn't a motor, because this will line up with the magnetic field. Maybe pass it and oscillate back and forth, but it's not a motor. For it to be a reciprocating motor, we're kind of in a world of hurt here. We need to engineer a solution. Now, does everybody first understand why this has to be true? Are we sure? All right. This is a very busy picture. And I hate to do this, but we need to consider something else that's happening here. The magnetic field created by the wire coming out of the board has got to be that way. This is the magnetic field created by the wire. Right? I use my right hand rule. It wraps this way, so it points that way. You good? Everybody sure? We've had some right hand rule mistakes. Into the board. Right? From a current carrying loop, we know that any current carrying loop is going to have a magnetic field through the middle that will be aligned. So this loop has a magnetic field that points this way. The torque on the motor is an attempt to line up the magnetic field produced by the motor with the external magnetic field. It's just like playing with magnets as a kid. The north poles are trying to line up together. What we would like to do is when the motor makes it to the top, it'd be great if we could get the magnetic field inside the loop to change directions. Which means when we get the loop to get all the way vertical, it would be great if the current swapped directions. If the current could swap directions, then instantly the magnetic field would flip and the motor would attempt to turn it over again. Its inertia should keep it moving, but then all of a sudden there'd be a new torque that would replace the old one that would change direction but would continue to push the motor in the same direction. You following what I'm trying to say? If not, this is really, really hard to see. So let's back out of this a little bit. If I can get down to where I was, let's get this thing off. I would like the wires, oh, that's too far. That's okay, let's get that back up there. Good. I would like the wires to make it from here to just past center. And when I make it just past center here, I want the current to switch. I want suddenly this to become the current that's into the page, and this to become the current out of the page, because then instantly this one gets the downward force and this one gets the upward force. Thus, my power stroke begins anew. The word power stroke is the word given to, generally to internal combustion engines, to talk about the part of the stroke where the gas is ignited and the expansion of the gas does work on the piston. Now, in a 4-stroke engine, only one of the strokes is the power stroke. The other 3 either are intake or exhaust or compression, which means no energy is given to the motor during the other 3 strokes. That means a quarter of the 4-stroke engine is only the part where there's power applied to the motor. You guys who've done any kind of work on cars, know anything about cars, understand we use the momentum of the engine to bring the gas in, bring the air in, and then compress that gas before ignition, and then exhaust that gas after it's been ignited. So you only get power in a quarter of the stroke, which is why you can't have a 1-piston car. There's not enough momentum to keep the car going. 3-piston cars are hard. They make them. But generally we have 4-piston cars. That's purposeful, so that one of the pistons is always applying power to the crankshaft all the time. Electric motors have to work in a little different process here. For them to be able to provide nice uniform power, they can do so by having multiple loops at a time. Most electric motors aren't a single loop. They have multiple loops so they can provide continuous uniform power all the time, with each of the different loops always being in a power stroke configuration. That's how you build a good motor. You engineer a good motor that way. We're not going to build good motors. We're going to build adequate motors. So let's talk about building our motors.